Well, hello, and welcome to today's class, which is class 17, which is going to be programming TCPIP. So last time we kind of looked at how the packets and datagrams were organized, how they layered up, wrapping inside of one another, application data, TCP packet, IP or TCP datagram, IP datagram, and then finally an Ethernet frame or packet being wrapped around that. And those outside layers get stripped off for the Ethernet level to go to each hop. It has to put a new hardware address on there, unwraps it, figures out the next address it goes to, sends it along by wrapping it in the next address. And that could be wrapped in something other than Ethernet along the way as well. But the IP part gets stripped off too, and then the time to live gets reformed and it gets put back on. There's not a lot of other changes in the IP layer or the TCP layer, but note that the reason for layering it from application outwards using something that approximates the OSI model is because that allows it to very conveniently strip off just what we need to and then route it and then add the next packet layer back on. So we're going to look at how we're going to write code that does this in a second. And in practice, the way that we're going to go about this is we don't have to worry a whole lot about the datagrams. There's an API that kind of does that for us. We just have to know how to use that API. And we don't have to worry about how the datagrams are formed. We don't have to worry about how they're sent. We don't have to worry about how they're routed or the stuff is stripped off and reformed as they're traveling. All we have to know is how to use this programming library that lets us do that. So to program TCP/IP, we're going to use the sockets library, which has been around for a long time. We'll look at the history of that here in just a second, but the idea is this is probably the oldest TCP/IP library that was widely adopted and used, and that's what most languages and most environments that you do TCP/IP programming within are based upon. So even if you're using a high-level language like Python, it still sits on top of the sockets library. So we're going to spend quite a bit of time looking at the sockets library, but we're going to look at it at a little bit lower level than something like Python uses it. Okay, so socket programming, that's what we're going to look at today, is how do we program sockets. So in practice, again, we don't have to worry much about that. We just have to know how do we talk to the socket programming library. All right, sockets, one of the most widely used network communication methodologies and libraries. It's a library that makes use of or can make use of multiple underlying network protocols. So it was a library that doesn't just necessarily work with IPv4 or IPv6, meaning TCP/IP and UDP. It also can be used for other kinds of networks as well. So the library itself was designed to be multi-network, not TCP/IP specific, but TCP/IP, UDP, IP are all supported. And that's what we're going to focus on. And since that's what the internet's built on, we're going to focus on that, but note that it supports these other things as well. It's also important to note that sockets, that library is designed to support multiple modes of communication, both kind of session/stream-based, like TCP, and also datagram-based, like UDP. In other words, remember the difference between those. A stream handles the reliability aspect of it. It handles making sure that no packets are lost. It handles making sure that the sequence numbers that are on the packets come in the right order. Any of them that are missing will get re-requested. So that's stream-based. You stuff data into the stream, it comes out the other end, and it's reliable. It also supports datagram-based methodologies, meaning that you basically just create a packet or a datagram and send it. And it's unreliable, meaning that you don't know if it got there or not. You know that you sent it, but you don't know that it actually ever got received. And you might say, well, why would we ever want something unreliable? Why would we want to use datagram-based when this does work for me to guarantee that data was sent and received? And the answer to that is performance. That TCP, it takes additional overhead to send things, to verify that they got received, to wait for a timeout when something isn't coming and re-request it. When something was missed, all of that has overhead associated with it. And if we want something to be really fast and have very low latency, we want to program that at a little bit lower level. So UDP is what we would use for something that needs to be more real-time or have low latency associated with it. And we're going to come back to this issue later on when we talk about programming game servers, which we're going to do toward the end of the semester. We're going to look at how would you write code to implement a game server. And we're going to use UDP for that. You could use TCP, but again, it can be slower because of all that additional overhead and the back and forth of traffic to re-request things and wait for timeouts. So TCP is probably not a good choice for something that needs to be close to real time, like a first-person shooter. But TCP might be perfect if you have like a turn-based game, like a pool game, billiards game, or maybe you have a turn-based game like chess or something like that. Reliability matters, not speed. But for something like a shooter, a massively multiplayer shooter game, something like Fortnite or one of the Quake games or Destiny or something like that, then you would want to probably use datagrams. We'll talk about that later on. Now, also, it's important to note that most of the internet is built on top of sockets programming. When you're using a web browser and connecting to a server and you see a page come up, the web browser and the server are using socket programming to do that. And if you're playing an online game, socket programming is doing that. If you're streaming Netflix, socket programming is doing that. If you're logging into Discord and sending chat messages back and forth, socket programming is doing that. So sockets that are largely what govern the communications that happen on the internet. The internet, largely, it's TCPIP or UDP IP. And sockets is our interface to talking to that TCP/IP subset that the whole internet is built on top of. All right, so sockets programming. First off, let's define what a socket is. So socket, we can think of that as a connection to the networking subsystem on the machine that you're on. So in other words, a socket is your way of talking to the network infrastructure or the network subsystem that's on your machine. So before we can do anything else, we need a way to talk to that API. We have to create a socket. So the socket that we will, once the socket's created, we use that for all subsequent calls that we want to do from that application. Now, you could have applications that open more than one socket and they talk to different things. That's okay. But the idea is you create a socket, you talk to that subsystem using that. Now, the original Berkeley sockets was written in C for Unix, so that's where we're going to start. We're going to look at what are called the manual pages or man pages for the different functions. And the reason I cover it this way is this is the man pages. If you have like a installed Linux distribution or any other Unix distribution, chances are that it has those manual pages. It comes with what are called the man pages or the manual pages, and those have the API reference built in. So this is a good way if you forget how sockets programming works, you can always refresh your memory by looking at the man pages for those different functions. So we're going to start with a man page for the socket function. And the reason we were looking at it at this lower level, at the C language level, is twofold. One is that's what Berkeley socket started. That's what most commercial software is doing at the socket level. And the second reason is all of the other high level things are kind of wrappers around that or sit on top of that or use the same methodology. There's a couple subtle differences. Maybe in Python, some of the things are a little bit easier to do because we don't have to worry as much about data types and things like that. But it's the same underlying sockets library using the same paradigm and the same kinds of function calls that we need to call to make the same kinds of things happen. So that's where we're going to start. So let's look at the socket function. So the socket man page, and this is from the Linux man page, the name of the function is socket, and the description is create an endpoint for communication. That's what we talk about. It's creating a connection for us to talk to the communication subsystem. So what do we need to do? Well, we pass to it the domain, the type, and the protocol, which are all integer values, and it returns to us this integer. And if you read the description, it says socket creates an endpoint for communication and returns a descriptor. Now that descriptor, you can think of that kind of like if you're used to the fopen function in C that opens a file and returns a file handle or a file pointer. It's kind of like that. This descriptor is our unique, you can think of it like a serial number or the ID number for that socket that we're going to use in the future to communicate with that. But let's look a little more closely at these three parameters: domain, type, and protocol. All right, so let's start off with domain. So the domain argument, then this is again from the man page. This is stuff taken directly from the man page. So if you forget all this, you don't have to look at this. You could type socket man page into Google. Or if you're on a Unix system or a Linux system, you go to the command prompt and type man socket, and this stuff will all come up and you can read through the entire man page. But you'll notice that the first parameter that this takes, first argument, is domain. And that specifies a communication domain, which is the kind of communication we want to do, meaning what protocol family is it that we're going to use for communication. And the available families are defined in this other header file. And here are some of the currently understood formats. You'll notice here's AF_Unix, AF_local. Those are used when we're not talking over the internet, but talking from one process to another process directly. Something we talked about in the, if you're in the concurrency class, we talked about that in there. But AF_INET is an IPv4 protocol, AF_INET6. And then there's IPX, NetLink, X25, AX25, ATM, PVC, AppleTalk, AF_packet, which is a lower level interface. But you'll notice that the one that we're going to be primarily focused on is this AF_INET. That's the typical IPv4 internet protocol. And most, even places that have IPv6, they have a way to fall back and still support IPv4 addresses. So we're going to focus on AF_INET for right now. That's the TCPIP. AF_INET6 is also TCPIP, but with a new addressing scheme. But let's focus on AF_INET. Now the next thing there is the type. That says the socket that we create will have the indicated type. And you'll notice the two that we're most going to be concerned with is sock_stream, which is sequenced, reliable, two-way, connection-based byte streams. And then sock_dgram, which is a connectionless, unreliable messages of a fixed maximum length. So these are like letters that are being sent. This is like a stream or connection that has been opened. But again, datagrams can be less, have less overhead and be much faster, even though some might get lost, which could be important for real-time things. We'll come back to these later. There's also this sequence packet, which is a sequenced reliable methodology that still works with datagrams of a fixed length. Again, that could be useful for games where you need to make sure you don't drop packets. There's a little extra overhead here compared to datagrams, but not like there is with a stream. And then there's a sock_raw and this reliable datagram layer that guarantees delivery, but not necessarily ordering. So for a game server, sequence packet or RDM might be good, but datagram, we could build our own sequencing, our own reliable layer if we needed to on top of that, which is what these have already done for us. But the two we're going to be using in today, or the one we're going to be using today, is sock_stream. Notice there's also something down here, the sock underscore non-block. That sets this O non-block flag description. That means that future calls using this socket won't block. In other words, you could set it up so when you try to perform a send or receive rather than blocking and waiting, it'll continue on. All right, let's look at the third parameter. We'll talk more about that at a later time. All right, the protocol. That specifies what protocol is going to be used. And normally there's only one protocol for every socket type. So for the most part, we're going to put 0 there. And one of the things that I want to point out is if you read through that man page, and this is how I learned TCPIP programming, or how I taught myself TCPIP programming, is I started with that socket man page. And then in that man page itself, you'll notice it says, it gives us all of the information we need in here. It says sockets of type sock_stream are full duplex, similar to pipes. They do not preserve record boundaries, meaning that if you send a block of data and another block of data, it doesn't come in as this block and this block, it just comes in as a stream. A stream socket must be in a connected state before any data may be sent or received on it. So that's an important thing to note. We have to connect before we can send data. A connection to another socket is created with connect. So we call this connect function. Once connected, data may be transferred using read and write calls or some variant of the send and receive call. So I've kind of highlighted those to show you that these are other functions that are part of this API that we're going to end up probably needing to use. When a session has been completed, a close may be performed. And then there's also send and receive can also send what's called out-of-band data, which is like additional data other than stream. And we'll not worry about that right now, but note that the important parts here, connect, read, write, send, receive. Now you might ask what this 2 in parentheses is. That's the part of the man pages that, or the section of the man pages, which is kind of the programming reference part of this. In other words, there might be other commands called send somewhere. I don't know, maybe for sending mail or something, but the programming reference for sockets, it's in section 2 of the man pages. So to get that, you could type man space 2 space and then send, and you get this man page for the send command. Now, continuing on, it says the communications protocols which implement a sock stream ensure that data is not lost or duplicated. And I'll let you read through the rest of this. I'm not going to read this whole thing to you. I just posted the man page stuff in here. But notice that sock_stream takes care of ensuring that there's no lost data, there's no duplicated data, there's no data that's transposed. In other words, what you feed in is what comes out the other end, and it's guaranteed to be the case. Now, down here, well, there is one other hint here. Sock_sequence packet sockets employ the same system calls as sock_stream sockets. The only difference is that read calls will return only the amount of data requested, and any remaining in the arriving packet will be discarded. So notice also it says, also all message boundaries on incoming data are preserved. That could be useful for something like a game server. But for the most part, we're going to use sock_stream. Also sock_dgram and raw sockets allow sending of datagrams to correspondence named in send to or receive from. So there's 2 other functions that we might look at, which returns the next datagram along with the address of its sender. So sock_dgram, fixed size or fixed maximum size packets get sent and received as blocks of data as they're sent, but it's unreliable. And then you'll notice the return value for the socket function. It says on success, a file descriptor for the new socket is returned. And on error, a -1 is returned. And this global variable errno, ERRNO, is set to some integer value that says what the error was. Now, what are some of those errors? They're listed down here. Permission to create a socket was denied. There's also the protocol that you requested is not supported. In other words, the machine you're on doesn't have that protocol. But for the most part, creating a socket will work because you're just saying, I want to talk to the underlying network system, and I want this domain, AF_INET, this type, the sock_stream, and protocol, most cases, will be 0. And it says, sure, I'll talk to you about that. I'll open that. But that does not connect to another machine yet. So creating a socket in code, here's some code to do that. So in other words, I'm going to create this socket descriptor called mySocket. It's just an integer. And here mySocket equal socket. And then here I'm making a AF_INET, sock_stream. And there's my protocol 0 at the end. And then I'm going to have an if statement that says if my socket is equal to -1, then we have some error message. It gets printed out. We should handle that error there. In other words, I could not talk to the network system. This function told me no when I tried to open a socket for this address family of that type of connection and that protocol type. So the idea here, also if you want to use, make a UDP, we'll talk about UDP, like I said, later on in the course when we get to talk about game servers. But notice the only difference is we put sock_dgram instead of sock_statement. But the socket call is the same. We just call it with a different connection type. One other thing to note is if you create a socket, you should always check the return value of that, not just assume it was created. There could be something wrong, and you'd want to more gracefully handle that in your code and print out some error message rather than having it crash later on in your code. All right, now that we have a socket, we need to decide if we're going to be the client or the server. Now, what's the difference? A server, you might think it's sending data out to things, but really the client could be sending data. The difference here is which one originates the connection and which one is listening for incoming connections. So a server uses its socket to listen for and accept incoming connections, and a client connects to some listening server. So that's the difference. A server is just waiting for packets to come in to create a connection from the remote end, and the client is the one originating the connection to the server. But once the connection is created, data can be exchanged either way. It could go from server to client, it could go from client to server. It's really up to whatever application you've designed, what order that goes in and what data gets exchanged. And then at the end of that, when the client is done or the server is done saying what they have to say, they can shut down and close that connection. As a quick reminder, for that to work, we need to have a server, which is listening, and the other end has to be the client, which is connecting. And so here I've put this little diagram. Let me hide my face on the video screen here so you can see the whole thing. But on this side here, I have put like the function calls that are needed for the server. These are the socket calls, and here are the ones that are needed for the client end. You'll notice one thing, they both start with a call to socket. They both create a socket, and then the client immediately calls connect, and then calls write, and then read, or read and then write. It's up to the application what order this happens in. And then when they're done with that looping around, either reading or writing, then they return back to outside of the loop, and then they close down the connection. Now on the server side, before anything else happens, we create a socket to talk to the network system, but then we do bind. We'll talk more about bind in a second, but what bind does is it essentially says associate this socket with a particular address and port number that we're going to listen on. And then we start listening on that port number. So then we call listen. So now listen is waiting for connections on the incoming address and port number that have been bound to with bind. And then we call accept, which actually waits for a connection to come in. When a connection does come in, we accept it, and now we have our connection. So now that we have a connection, we do the opposite of what they did. If they wrote, we read. If we write, or if they're going to read, we write. We exchange data. Once we're done exchanging data, we, with our write and read, we can do a read, which will give us an end of file notification, and then we can close it, or we could just hit close here without trying to do that additional read to get that EOF notifications. But notice you can have the client tell the server when it's done by sending that EOF automatically when it reaches the end of the file, and then it can close. So we're going to focus on the client side first, so this side over here. So let's take a look at that. All right, so on the client side, we're going to use the connect function. And so here's the part of the main page for the connect function. It says name of the function is connect. It initiates a connection on a socket, so we already have to have a socket. So here's what the function prototype looks like. Connect int sockfd. And then we have this structure, this sock ADDR pointer called ADDR. We've got this sock length underscore t for the address length. And essentially what we need to do is pass those things to this function, and then it's going to return a value to us. So let's look at the description here. The description says the connect system call connects the socket referred to by the file descriptor. In other words, that was a socket that was created by our call to the socket to create that initial descriptor, to the address specified by ADDR, which is the second parameter. The address length argument specifies the size of this address ADDR struct. The format of the address in ADDR is determined by the address space of sockFD, or socket FD. In other words, it depends on the type of socket we're creating. So AF_INET socket addresses may look different than other address family addresses, and that's why they created this generic sock ADDR. In our case, this is going to be holding a TCPIP type address. In other cases, it might be holding some other kind of address. But again, that's because they made the Berkeley sockets somewhat generic because it supports a whole bunch of different ways of doing networking. Now, if the sockFD is of type sockDgram, then ADDR is the address to which datagrams are sent by default, the only address from which datagrams are received. If the socket is of type sockStream or a sequence packet, this call attempts to make a connection to the socket that is bound to the address specified by ADDR. So in other words, if we do sockStream, it's going to connect to the other end. If we do dgram, it just sends it out. And the return value, again, a -1 on error. If the connection succeeds, you get a 0 back from it. And it sets that error node to tell you what the error was. All right, so here is some client code. And notice this isn't a complete C program. It's not wrapped inside of a function. But this, I think, illustrates how you make a connection. So here, there's my socket. And then I created this struct sock ADDR_IN. Notice _IN is different than what this wants passed. This just wants sock ADDR. The _IN here is an internet type socket. That's why that _IN is there. It's a little bit different structure that we're going to send in to that function. So here's the same code we had before to create a socket. We're creating an internet stream, so TCPIP. And then if we made it past this if statement, it'll say socket created. And now we're going to fill in the address that we want inside of this. So server.sin_ADDR.saddr. This is the part where we plug in the 4 bytes of the IP address. And here I just looked up the address for google.com. It's probably different today than it was when I looked this up previously, because they do load balancing by switching the address, and they'll switch the DNS name around. But this might go to Google if you try it. If you wanted to, you could look up the current address and then plug that in there. Or if you had the address of some machine, like you wanted to test this on your local machine, you could just do like 127.0.0.1, the local host address, and connect to your local machine. But the local machine would have to have a server running on it, which doesn't right now. So this code is going to connect to Google server. Server.sin family is INET. Server.sin port is 80. That's the normal HTTP port that's used. And then we call connect. Here's connect being called. We pass in the socket that we got from up here. We pass in the address of this structure. But notice this structure had a slightly different type than the type that it called for, so we cast it as a pointer to that type of structure here. And again, the reason for that was that the functions in Berkeley sockets were designed to work on a range of different networking subsystems and addressing types. Again, it was designed to be a generic kind of networking interface, not just for TCP/IP communication over the internet. And so they created this generic structure here. We pass in our specific type, but this function expects this generic type, so we just cast it as that. And then we pass the size of that structure in, which you could have said size of struct sock ADDR_in here as well. And then if we get something here that's less than 0 or a -1, that means that it failed. So we print out that it failed and say we couldn't connect. Otherwise, we say we connected. And now that we're connected, we would do something with that socket afterwards. Okay, so that's the client side for getting connected. If we're going to write our own server, Then remember we had a few extra things we had to do. We had to bind, listen, and then accept to wait for an incoming connection. So what each of those do, bind, it binds an address, and again, these are from the man pages. Bind binds an address to a socket, and in other words, it's saying associate that socket to some IP address and port number. Listen, after we have used bind, then we call listen, and what listen does is it listens for an incoming connection on that socket. And there, we'll look at how listen works in a second. But once we're listening, then when a connection comes in, we can then accept that connection. And then once we've accepted the connection, now we're at the point where we're connected just like we were after the client call. So let's look at each of those three functions in a little more detail. Let's start with bind. Again, from the man pages, here's bind. Bind accepts the socket that's already been opened. And then again, the structure for this address, and then the address length. So very similar to what we saw with connect, but we're not connecting to a remote machine. This is our local machine that we're calling bind on here. So the description, when a socket is created with socket, it exists in a namespace or address family but has no address assigned to it. Bind assigns the address specified by the ADDR parameter and associates it assigns the address specified by ADDR to the socket referred to by the descriptor, and then ADDR lane specifies the size in bytes of the address structure pointed by ADDR. It says traditionally this operation is called assign a name to a socket. It's normally necessary to assign a local address using bind before socket stream may receive incoming connections. So in this case, what we're doing is we're saying associate the socket, which was just a way to talk to the TCPIP subsystem or the networking subsystem, associate it with a particular local address and port number, so future communication will happen using that port number. The actual structure passed to the ADD argument will depend on the address family. It's defined something like this. So it has the family, and then it has 14 bytes of data. And that's why we were using that struct sock ADDR underscore in. And so this is the generic version. It always has a family as the first 2 bytes, and then after that, it has the actual data. And like the other functions, it returns the bind function on error returns a -1, and on success, it returns a 0 in this case. So we'll come back to that in a little bit. All right, but let's look at listen. All right, listen, and again, from the man page, listen for connections on a socket. So listen, sock FD, backlog. It says listen marks the socket referred to by sock FD as a passive socket. That is a socket that will be used to accept incoming connection requests using accept. So in other words, this is setting this as a socket that's going to be used for accepting connections that come in. So it's almost like you can think of listen as turning on the ringer to the phone. It says the sock FD argument is the file descriptor that refers to a socket of type sock stream or sock sequence packet. The backlog argument defines the maximum length to which the queue of pending connections for sock FD may grow. Now, that second one, the backlog parameter, is how many incoming connections can be pending that haven't been accepted yet before that socket starts rejecting incoming connections. And if you have something that has a lot of traffic coming in, you'll want a little bit larger backlog. But generally what happens, a connection comes in, we accept it, and then there's a loop that then goes back and accepts another one, accepts another one, accepts another one. And so if you were to set the backlog to 1, then you really won't, you'll accept one and it'll reject future ones. But if the internet was built like that, then you'd have a high traffic server like google.com constantly rejecting connections because it would be busy handling someone else's. So what they did is they built this kind of backlog buffer. So as people try to connect, they kind of build up. So think of that like you call a phone number and they're like, you are currently number 4 in the waiting list. So it's kind of like that. So the question is, how deep does that waiting list go until you get a busy signal? And that's what we're specifying with backlog, the backlog parameter. Again, on success, 0 is returned, or on error, -1 is returned. So this is just listening. This hasn't actually accepted a connection yet. We're just listening. All right, now we're up to accept, the one where the connection actually gets created. And with accept, we have, again, starts off with the socket file descriptor. The next one is the address, and the next one is the address length. Now this address here and that address length are a little bit different. Notice that these are both pointers, because this one was a pointer before, this one was just a value. But you'll notice that what is happening here is, well, let's read the description from the man page. The accept system call is used with connection-based socket type, sock stream, subsequent packet. It extracts the first connection request on the queue of pending connections for the listening socket, creates a new connected socket, and returns a new file descriptor referring to that socket. The newly created socket is not in the listening state. The original socket, SockFD, is unaffected by the call. Now, there's a little bit to unpack there when reading through that. In that, you'll notice we pass in the listening socket to it. But what it returns to us on success is the actual socket file descriptor of, and I see there's a mistake there on the bottom. I don't know why it says on 0. On success 0 is returned. That must be a cut and paste error. Here, I'm just going to put new FD as return. We'll talk about that in a second. Okay. The argument SockFD has to be a socket that's already been created with socket. It's already bound to an address of bind and is listening for connections after listen. So again, the man pages are telling us what we need to do to use this thing. The argument ADDR is a pointer to a sock address structure. The structure is filled in with the address of the peer socket. So in other words, whoever connected to us, we get their address filled in. And you can put a null there if you don't care about the address of who's connecting, but you can get the address of whoever connected to you. That's going to be their IP address that gets filled into that. And then notice the last one, the ADDR length argument, is a value result argument, meaning you put a value into it that says how big in bytes the structure is. And then on return, it contains the actual size of the peer address, which is generally going to be the same as what you put in. All right, so here's server code that would go along with that. And again, this is just a snippet. It's not inside of a function, so it's not valid C code in an entire program. It's just a snippet. But you'll notice we have my socket. We also have new socket. And now I have two addresses here. I have my address and I have their address. So mine is the address of the server. Their address is going to be when they connect to us, I'm going to get their address. And then I have this integer, their address size. Okay, so looking through this code, same as before, we create a socket. We fill in our address. If you put a 0 in there, it'll use the default local address. The address family AF_INET. And since this is the address I'm listening on, I need to specify what port I want to listen on. In this case, 0x1234. And you might say, what's this htons function? That's a new function that we haven't seen before. But that stands for host to network short. And the reason for that is different machines represent integers in different ways. There's a big endian representation, and then there's little endian, where the most significant and least significant bytes are backwards in memory. To make sure that different machines, the endianness of the architecture of the machine doesn't come into play, there's this host to network short function that no matter what system we're on, it'll always put them in the right order for that system. It's putting in the network byte order, not the machine-specific byte order that the local architecture is using. Okay, so after that we bind. We're binding this address to that socket. And then after that, the socket's bound. So then continuing on, we want to listen with a backlog, in this case of 10 pending connections. So I say listen to 10. And if that's not -1, then we're listening. And now we have their address. We pull the size of their address into that to fill in the size, because remember that was a value result parameter. And then down here, we call accept. We pass in the address of the machine that we want, that structure for their address. And remember, accept is going to block and wait for a connection to come in. And then once it's connected, then we'll get down here. Otherwise, it'll sit here forever waiting for somebody to connect to this server. But as soon as they connect, it prints out connection accepted. And now we're ready to do something with that connected socket. Send, receive, and eventually close it. So after that, with those two sections of code, we would be connected to the other end. So once we're connected, we can exchange data using send to obviously send data to from our end to the other end, receive obviously to receive data that was sent to us. And note that a send on one end has to correspond with a receive on the other end. In other words, if the connection gets created and they both do a send, they're both going to be stuck there. So in other words, you need to come up with an application level protocol that does send from one end to the other, receive from this end to that end. So we need to pair up a send with a receive or receive with a send. All right, let's look at the send and the receive function in a little more detail. And the way that works, you'll notice with send, it's send a message on a socket. Send, you specify the socket number, a pointer to the buffer we want to send, a length of how many bytes in that buffer we want to send, and then this last thing here is flags, which can specify a set of flags for how we want that send to occur. And you'll notice that basically we're just passing an address and a number of bytes, and it's going to send those for us. And on success, it's going to return the number of bytes that were sent, and on error, it's going to return a -1. And one thing to note is if the return number of bytes was not the same as the length that we tried to send, we have to call send again with the remainder of that, the next block of bytes after that. But the cool thing about send is when this returns and says success, we are guaranteed that that data got received on the other end, because that's what the SOC stream actually does. It's what part of TCPIP does. It guarantees reliable transmission. So when it says yes, this was sent, it doesn't mean we just dropped it in the mailbox. It means the other end actually got that. So it's kind of like a return receipt or certified mail that gets sent, and you get a thing that says that person definitely got that. All right, the receive function works the same way. The only difference here is this is the buffer that data is getting read into, and this is the number of bytes that came in. Or this is the maximum size of that buffer, I mean. And what does it return? It returns the number of bytes that were received. So this is the number that were received. This is the maximum size we could fill into that buffer to make sure we don't overrun it. And then there's also flags here. We're not going to talk about the flags right now. Also, receive could return a value of 0 when, in other words, it's kind of saying, it's not saying there was an error, it's saying 0, meaning that the other end has shut down and they've terminated connection. So that's where I talked about earlier, that kind of end of file condition coming through. That we could say, if I called receive and I get a 0, we know the other end said, hey, I'm done talking, and I've shut down. That's different than an error. That's saying, I'm done. You can stop waiting. All right, so now that we've exchanged data, we want to close the connection down. Now, depending if you're writing this code for Unix or Linux or Windows, it's done a little bit differently. With Unix and Linux, it's done with a call to shutdown. In Windows, it's done with a call to close socket. And most of the functions in Windows mirror those of the Berkeley sockets library. And that's because Windows, Microsoft, when they went to create their TCPIP subsystem, they such a system already existed for Windows, it was easy for them to just kind of copy that methodology from the way that Unix did that with Berkeley sockets. And there are a few subtle changes for doing this, but it works the same under Windows, at least from a conceptual standpoint, and it has mostly the same function calls. We'll look at that Windows-specific implementation in just a little bit. But before we do that, let's look at the shutdown function call. The shutdown function call for Unix and Linux, we basically pass in the socket we want to shut down, and then we just pass in how we want it to shut down. And there's 3 ways we could shut down just the read end, shut down just the write end, or shut down the whole thing with shut, read, write. And then further receptions and transmissions will be disallowed if we do that. Again, on success, 0. On error, -1. On Windows, if we use close socket, we don't have to specify the how. We just say, hey, I want to close the socket. We pass in the socket that we want closed, and then it closes it. And if there's no errors, returns a 0. Otherwise, the value of socket error is returned, which is actually the same as -1. Okay, so here's an overview of that entire connection process. On the client, opens a socket, fills in the address information, connects to that address. And this is address information of who we want to connect to. Connects to that address. Once we're connected, exchange data with send and receive. And once we're done, close the connection with shutdown or close socket if we're on Windows. On the server end, open the socket, bind it to the local address, listen on that socket, accept a connection using accept. Once the connection is accepted, we exchange data using receive and send. And then when we're done, close the connection and call shutdown or close socket if we're on a Windows machine. So that's it. Those are the function calls we need. Here's that overview of what we talked about earlier with socket comes first. On the server end, bind, listen, accept. Now we're waiting. Socket connects to one of the waiting threads. And hold on 1 second, I gotta take this call and I'll be right back. Okay, so on the server side, we have to do all this stuff, and then once we accept we're connected, on this side we just socket and connect, and we're connected. And this is what's happening when you're using a web browser, or really doing anything on the internet. That when you connect to google.com or Reddit or whatever, they already have server code that's running that's waiting to accept connections. They're listening for connections, waiting to accept them. When you type in the URL on your browser, it connects to that address. Now, there is a mystery there, like how does it go from a name like reddit.com to the actual address, which is some block of 4 bytes, 146.85.1.1 or whatever. That's something we're going to investigate in a later lecture. But in other words, this is what's happening on your web browser. When you connect, once it's connected, it exchanges data with the web server, gets the web page content, renders it on the screen, goes back and downloads pictures, renders them on the screen, goes back and does other things. And then once the connection is done, then we disconnect. And in a future lab, we're going to look at creating our own web server. We're going to look at how HTTP, how that protocol works at the application level. But that's more in this section here. What do we read? What do we write to do that? And on a web browser, it writes the request for what it wants. The server reads that request, gathers the data to send the response, sends the response, and then the browser renders it on the screen. And when the connection's done, close the socket, close the connection. One little bit of mystery here is, here, let me back up and look at that code here. The one thing here that's important to note is when we accept the connection using accept, we get a new socket descriptor that's identical to the one that was listening, but is not the one that was listening. In other words, and the reason for that is that frees up the listening socket to handle that backlog. In other words, we accept one, gives us a new descriptor, we can then communicate on that. So think about that like a main phone line for a company that rings through, and then it gets automatically transferred to an available receptionist or tech support desk that can handle that. So in other words, you don't want to have the phone ringing busy. You want to be able to farm out each of those connections to workers, and that's what's happening there. Now, programming TCP/IP in Windows, let's spend just a little bit of time to talk about that. And before I do that, I'm going to pause for a second and fix the page numbers on the bottom here. So give me 1 second. Okay, a couple things about that. Back to programming in Windows, TCP/IP programming in Windows. There are a few different things we need to do to make all that work under Windows. That we looked at the Unix min pages, and the good news is that the Windows API for doing network programming was completely based on the way that Berkeley Sockets was created. In other words, Berkeley Sockets already existed. When Windows added their networking support, they're like, well, let's just copy what they already did. So they kind of ripped off the way it was done in Windows or in Unix. And the way that they did that, though, there is one thing that's different. In other words, you have to use this winsock header instead of sys/socket.h. So we have to include this instead of that. That's the first change. The second thing is, before any socket functions can be used, we have to initialize winsock, which winsock is the kind of Windows Berkeley Sockets API or library. It's implemented as a DLL, so we need to initialize that DLL. And the way we do that is we call this WSA startup function. Here's the code that does that. So we do this WSA data, and then we call this WSA startup function. And then this make word is specifying the version that we want. And this address of WSA fills in some information like a descriptor into that WSA variable. Now, if that returns something other than 0, then it failed. If it returns 0, it succeeded. Now, one other difference is rather than that global errno variable, that EERNO, we call this WSA get last error, and it gives us the error number. So that's another difference. Oops, I should have hit Shift F5 a while ago on this. Okay, now a couple other differences. I just mentioned this one, but use WSA get last error to get error codes rather than reading the errno global variable. And then close the socket with close socket instead of shutdown. We already talked about that. And then when we're done with winsock altogether, we call this WSA cleanup function. And that's it. Those are the only differences. Everything else works the same. In other words, bind, or the socket function, bind, listen, connect, send, receive, all of those work the same way as they do in Berkeley Sockets, because the winsock API was essentially, they ripped off the way that it was done in, or copied, or made their system compatible with, however you want to think of it. They copied the way it already worked in Unix. So everything else works the same. So you should now be able to write some simple client-server programs in either Unix, Linux systems, or in Windows systems. And here's a complete working example. This example is going to connect to Google via HTTP and request the default page. So let's go through this. So this actually is a full program, and I've did this for Windows. So this is the Windows version. So if you're on Mac or Linux, you would have to make those, undo some of those changes. So instead of using winsock, you'd use the other header file, and rather than having this WSA data and this WSA startup thing, we would just get rid of all that because we wouldn't need it in Windows. And then shutdown would be different. The rest of it would be the same, but let's walk through this code. So this is going to receive up to 5,000 bytes of data from that. So here's the main. The first thing we do, other than creating all these things, I create this server reply buffer of that size, 5,000 bytes. And Google might return more than 5,000 bytes. I'm just going to receive the first 5,000 bytes from their web server. And then you'll notice I call WSA startup. If that succeeds, we know that winsock has been initialized. I then create my socket. If that succeeds, then we continue on. After that, I fill in the address structure. Here's the address I looked up of Google. There's the address family is internet, or AF_INET. The port we want is port 80. That's the default HTTP port. After we filled in that stuff, we connect. If connect succeeds, it'll print out that it was connected. And now we're going to send this get request, get the root folder. We're requesting at an HTTP TCPIP3201. It's a little bit outdated now. In the lecture about web servers and web browsers and HTTP, we'll talk about that. But then we do a send where we're sending this request. And then we wait for to read the reply. And if that succeeded, we just print out how many bytes were received. I place a null terminator at the end of that string, and then I print out whatever their reply was. So I'm going to get whatever it's not going to show up obviously as a web page, it's rendered. This is just whatever the response was from the server. After that, we close socket, call WSA cleanup, and return that value 0. Now, here's a simple TCPIP web server that would make the other end of that connection, but I'm not running it on port 80. And you'll notice this does the same kinds of things for the web server, but we call WSA startup. We create a socket. We fill in the address of our machine. We call bind using that address. If that succeeds, then we call listen. If that succeeds, then we're listening. And now we hit connect, which is accept, which is going to wait for a connect from the other end to come in. If that connection comes in, it's going to fill in the address of who connected to us and the address size of that. And if that succeeded and we get down here, then we call receive, which is going to receive their request. And then here we're going to call send and send out a response. Here's the response. We're just going to send out this hello world thing in the middle of the screen. And then we're going to say response sent, print out the message it was sent, which is this thing here. And then after that, close the new socket that was created on with accept, close the original listening one, clean up WinSock, meaning disconnect from the WinSock library, and then we're done with the main program there. So this web server serves one page and then closes itself down. Realistically, a web server would wait for other requests and serve multiple pages. This one only serves one. Okay, so for your lab, you're going to kind of combine the concepts from those two. I would encourage you to look at those programs carefully and look at what they're doing. But you're going to kind of, one way to do this would be to modify those and create it so that one program is going to act as the server. It's going to accept a connection on a port, and the client program is going to connect to that server. And after the two things are connected, they're going to exchange some simple data. So let's take a look at the lab sheet real quick. So let me switch over and bring that up. I thought I already had it open, but maybe not. I do not. So let me open that real quick. Oh, let me switch it so you can see what I'm doing here. Okay, so here's the lab sheet. And you'll notice you're going to be working individually on this, not as a team. And I want you to use Berkeley sockets in Windows. I want you to use C and WinSock 2 to do that. So you're going to write, and I'd suggest you could use any development you want, Visual Studio, code blocks. There are some different linking instructions you'll need for code blocks versus Visual Studio. I'll let you Google that and figure that out. But essentially what you're going to need to do is on the client side, you're going to open a socket, connect to the receive program or the server, send the message, Watson, can you hear me? And then close the connection. So this is actually a little simpler than we had with the version earlier where the browser connected to Google, sent a request, received a response. In this case, we're just going to connect and send a message and then close the connection. That's it. So you can take what we did in the other examples and kind of create this out of that. Now on the server side, why'd this jump to there? On the server side, we're going to open the socket, bind the socket to an unused port. You can pick whatever port you want, 0x1234 or 0x1010, whatever you want. As long as the one you connect to is the same as the one you're listening on or bound to, it should work. We listen for incoming connections, accept an incoming connection, receive the message that comes in and print it on the screen. So in this case, you should see the client will say, sending Watson, can you hear me? This will receive that and say, hey, I got a message. Watson, can you hear me? And then close the connection next to the program. Each program needs to include the necessary error handling and return values. In other words, after each of those function calls to something in Berkeley sockets, make sure to look at that incoming connection or look at the return value to say whether the incoming connection successfully was listened to or accepted. Make sure to check the return values of all of these. If it fails, make sure to print out what the error was or print out some error number, at least that an error happened. One other thing here is that your programs will be running in Windows. You might need to configure your Windows firewall or other Windows security settings to allow that connection. Usually what will happen if it's set up, it'll say, you'll get a box that pops up and say, hey, this program is trying to listen on the internet or access the internet. Do you want to allow it? Just click allow and it'll work. Or you might have to open your Windows firewall settings and then say, hey, allow this particular program to access the internet. So make sure the programs compile and work before you submit them, but that's pretty much all you need to do. It's a very simple thing. The server is going to listen for a connection. The client's going to connect and send a message through. The server is going to print it on the screen. They're both going to close down, and that's it. So if you want to run it again, you'll have to run the server again, run the client, and you'll have to run the server first because the client needs to be the one that originates the connection and connects, transfers the data, data gets printed on the server, closes. And you can do all this testing, even though this is network code, you can do it all on your local machine to test it by running the server first, running the client. The client will then connect to the server even though it's on the same machine. But you could also, if you have more than one machine and they're both connected to the same LAN, feel free to set it up so that they talk to each other, so that your laptop talks to your desktop, or your roommate runs the server, you run the client, they'll be able to talk to each other. And really, this could work across machines anywhere in the world, like to Google or anything else. So this is kind of a very simple, boiled down program that'll allow you to do that. Okay, so that's it for that. Let's go back to the presentation for just a second here. Okay, so we looked at the lab. That's all we're going to do today. I wanted to come in at under an hour. It's a little bit over, unfortunately. It's 2 minutes over and 44 seconds right now. But that's all I wanted to do today. That should give you an hour and 15 minutes to work on the lab, and you can get that done in that amount of time. So get it done today, even though it's not due till next week. Work on it, get it done. You can use the code that I have there kind of as a basis for that to get you started. But work on getting that done today. If you're having compiler issues where it's saying that the unresolved external for any of those socket things, Google how to get either code blocks or whatever development environment, what the linking process is needed for WinSock. And or if you're under Unix or Mac, then you'll need to compile that and maybe link to something else. Mainly in code blocks for Windows, you're going to need to add the WinSock2 library to your linker list of things that your linker is linking to. And I'll let you Google that and figure that out. But if you have trouble, let me know. I'm here to help. But try to get that working today, if at all possible. And that's all we're doing today. Working on that lab. Get it done. Next class, we're going to dig a little more into TCPIP, how the name system works. We'll maybe look at that a little bit. And then we're eventually going to move into some more complicated things with HTTP and how it works. And then we're going to move on into some game server programming related topics after that. So go and work on the lab and let me know if you have problems.